In this small tutorial, we'll talk about the differences between sequences and series. As we saw last class, sequences, which had the curly brackets, were these infinite lists, where each item in the list had a specific indexing variable, which here is given by this sloppily written n, but each item in this list, A1, A2, A3, and so on, corresponds to a specific n value or counter or index. This is different than series, which, as opposed to infinite lists, are these infinite sums. And series are written with this capital sigma, have a similar type of indexing variable, 1 to infinity, in some generating function, here a sub n. But instead of just listing out the a sub n's, in this case, we are adding all of them together. So a1 plus a2 plus a3 plus a4, and so on. So the big difference between sequences are infinite lists, and series are these infinite sums. And when we talked about convergence for these infinite lists, what that actually meant were these items really, really far down the list, they all start looking identically the same. For series, which we're going to focus on for the next few weeks, we're going to see that the idea of convergence is actually not as simple. So just to recap, for sequences, we were able to basically take a limit as n goes to infinity of that generating function for sequences, and if this was equal to a number that was finite, then we said it was convergent. The idea for series convergence isn't going to be as easy as we'll see in a couple moments. But before we do that, let's just go over a few examples of how to just think about infinite series. So as an example, let's consider the following series. This is the series from n equals 1 to infinity of, let's just do 1 over n plus 3. So if we're to write out the first couple terms in this sum or series, again, the first term would be when n equals 1, we just plug in a 1 for all the n's, and all the other terms we leave the same. So we have 1 over 1 plus 3. The second term, a sub 2, that we add to the first term would be 1 over 2 plus 3. The third term would be 1 over 3 plus 3. And we would keep doing this. So this is similar to how every single term in a sequence we indexed by this indexing variable n. For series, we're doing the same thing, except instead of listing out an infinite amount of items, we're adding together an infinite amount of items. So just as another example, this idea of adding an infinite amount of things is actually quite bizarre. When you think about it really quickly, how could the sum of an infinite amount of things come out to a number that's finite if we're adding together things that are not identically zero? But just as a quick reminder, we've actually seen this idea before. When we started thinking about the area under curves using, say, Riemann sums, we had this idea where if we're considering some integral, or we want to find the area under some curve from a to b of a function f of x, we started breaking this into specific partitions. And the way that we approximated the area of a to b of f of x, or the integral I should say, was basically by this finite sum of rectangular areas if we're doing something like left-hand rule or right-hand rule. So we had something on the right-hand side that basically said we had a sum. In this case, it looks like there are 1, 2, 3, 4, 5 different partitions. So say from n equals 1 to 5 of a function value f of x or f of xn times the thickness of each of those rectangles. And just like we said in class when we were doing Riemann sums, one thing that was better, instead of using, say, 5 rectangles, was, say, we use 100. And what's better than 100? Say we use 1,000. And what's even better than 1,000? Say 100,000, a million, a billion, and so on. And this led us to the idea where, actually, if we want to compute the true value of this integral, the true value is actually equal to the limit as the number of partitions went to infinity of the sum of each of those rectangular sections. So we have the little counter index is little n, and we're counting the number of rectangles as capital N. Probably a poor choice of notation, I apologize. But we're still doing the same thing, a function value at each little n index times the width of those intervals. And as we take the number of those partitions to infinity, we actually get back the definite integral, or the area under the curve of f of x between a and b. But what this actually has for us is an infinite sum. So we've seen this idea before of infinite sums actually converging to a specific number, and we call these definite integrals or improper integrals. But we've seen this idea come up when we talked about integration. Next, what we're going to talk about is start thinking about what we actually need to happen in order for an infinite sum to possibly or potentially converge.